Okay, so I'm not going to do a screencast for this because I prefer to write math by hand. So hopefully this works for what we need it to do. So I'm only going to show you that last problem we were working on because it seems like that's what gave us the most trouble. And that's that Fox Lane problem. So in A, the first thing that we're given is that Fox Lane is a 60-acre campus. And we're given the conversion factor there of how many kilometers are in an acre, kilometer squared. So for that one, we're given that 1 kilometer is equivalent to 0.004 kilometers squared. So in scientific notation, 4 times 10 to the negative third kilometers squared is 1 acre. Now, you can stop and solve right there and then go from kilometers squared into meters squared, but I prefer to just do it all at once. So this is another conversion factor that you should know. 1 times 10 to the third meters, or 1,000 meters, are equivalent to 1 kilometer. So remember, we're going from kilometers squared into meters squared, so you have to do that conversion factor twice. That way you cancel out the kilometers squared, but also so that you end up in meters squared. So now 60 times 4, we have 240 times 10. The negative 3 exponent here, the positive 3 exponent here canceling out, times 10 to the third meters, which is technically 2.4 times 10. Remember that exponent will increase based on the number of places you move the decimal. So times 10 to the fifth meters, and this was supposed to be squared. That's going to give us the area of the campus, and that's what they ask us to solve for in A. In B is when they start to bring in the idea of this storm, and they talk about a storm in 2005 that occurred before the construction on the campus. So the first thing that we know is that they give us that it's 10 centimeters of rain that falls. So remember here, our goal is to get a volume. Not only is our goal to get a volume, but we want volume in meters cubed. So we need to change the 10 centimeters into meters. So 10 centimeters, that conversion, 1 meter is equivalent to 100 centimeters. Therefore, 10 centimeters are actually 0.1 meters. Or if we're keeping this in scientific notation, 1.0 times 10 to the negative 1 meters. Remember, we're looking for a volume, which is length times width times height, but really that length times width is going to come from our area in the previous step, and that height is going to come from the amount of rain that falls, or what we just solved here. Now that we have length times width and height, we can solve for the volume. So we have 2.4 times 10 to the fifth meters squared times 1.0 times 10 to the negative first meters. Multiplying those, we get 2.4 times 10. Remember, exponents 5 minus 1, that would be to the fourth. And our units, meters squared times meters cubed. We are not done here. You can't stop here because it's asking us how much runoff is generated. And the problem goes on to say that at that year, at that point in time, we had 10% impermeable surfaces. So we need to multiply this number by 10%. In doing so, we're going to multiply 10% in scientific notation. And when we do that, we get 2.4 times 10. Remember, exponents again, 4 minus 1, 3, and that's in meters cubed. So that number represents the amount of runoff generated from that storm. In C is giving us a very similar problem, but now they're saying post-construction when the percentage of impermeable surfaces goes to 20%. Nothing else is changing though. The area of the campus is still the same. The amount of rainfall is still the same. Because those things are still the same, that tells us that we can use that 2.4 times 10 to the fourth of rainfall that we got here. That number is not going to change. What does change once again is the percent. So rather than 10%, we have 20%. So this time when we multiply, we get 4.8 times 10, again 4 minus 1 to the third, meters cubed. So essentially the point is, the more impermeable surfaces you have, the higher the percentage of runoff. When you get to D, D starts asking about the senior parking lot. And D is saying, okay, if this is the total amount of runoff generated, what percent of that came from the parking lot? So the first thing that you need to do is find the area of the parking lot. And that number is given to us in meters, so we don't have to do any conversions. We just have to find the area. So we have 80 times 300. Again, in scientific notation, because you're not using a calculator, we get 24 times 10 to the third meters squared, which again would technically be 2.4 times 10 to the fourth meters squared. So once again, that represents the, not the volume, the area of the parking lot. Okay, so now the problem is going to look similar to before. If I have the area of the parking lot, that's my length times my width, I need to multiply it by my height, which is the rainfall. Again, the amount of rain is still the same. So it's still 10 centimeters. It's still 1.0 times 10 to the negative first. So that's that 10 centimeters of rain. In case we forgot, this was the area of the parking lot. So when I do that, I get 2.4 times 10 to the third meters cubed. And now in our previous problems, we had to multiply this number by the percent of impermeable surfaces, but in this problem, it tells us that the entire parking lot is impermeable. It says 100%. So you don't need to do that last step. You don't need to multiply this by a percent. Therefore, you can stop right here. And just kidding, you can't stop right here because we need it in percent, but we know that this is the amount of runoff from the parking lot. So that last step that I almost skipped, for the percentage, we have if 2.4 is generated from the parking lot and the total amount was 4.8, then we know that 50% of that runoff was generated from the parking lot. Okay. From there, E and F go on to talk about the water treatment. In E asks us to solve for the total amount of untreated water produced, and it tells you in E that that is going to be the combination of the sewage plus the runoff. So that's literally what you have to do there. So our runoff from earlier was 4.8 times 10 to the third meters cubed. So all that is that total runoff we calculated. Plus, in the bullet points, it tells you that on average, the campus is going to generate 1,000 meters cubed of sewage daily. So all I'm doing is adding those two numbers together. That's all I have to do for this step. And I know it seems simple, but that's all they're asking you for there. So we get 5.8 times 10 to the third meters cubed of untreated water. Finally, in F, it says, okay, well, if that's how much is untreated and the total capacity that we can hold in this treatment plant is 5,000, how much is going to bypass the system? So for this, it may be easier to put it back into standard notation. So 5.8 times 10 to the third would just be 5,800. The capacity is 5,000. So we end up with 800 meters cubed of water that's going to bypass the actual system. And then G and H are just conceptual questions. So when you're solving these problems for the math, you need to keep in mind, you need to know how to calculate areas with conversions. Going from acres to kilometers squared to meters squared, or just kilometers squared to meters squared. You have to know that your volume here, really what you're doing is area times that height being the rain. You have to know that when you're calculating runoff, you have to remember that you are calculating volume, but you're also taking into account the percent of impermeable surfaces. And then you have to remember that when you are calculating how much water is going to bypass the system, remember to take into account the capacity of that system or how much that system can hold. The rest ends up as bypass. Hopefully this is helpful. Hopefully it makes it a little bit easier, and good luck.